Swayam Prabha. Digital India. Educated India.
Welcome to the next session on Pharmaceutical Organic Chemistry Paper 3. In Unit 3, we are studying about heterocycles, Part 1. In the second lecture, we will be studying about nomenclature of bicyclic systems and aromaticity of heterocyclic compounds. I am Dr. Balaji, currently working as Associate Professor in the School of Biotechnology at Jawaharlal Nehru University. This project is sponsored by DTH Swayamprabha, MHRD, New Delhi. In this session, we will be studying about the nomenclature of bicyclic systems, how to name bicyclic heterocycles, and we will also be studying about aromaticity of the heterocycles. We will also be studying some of the general methods of synthesis of heterocycles. In this session, we will be studying about nomenclature of bicyclic systems. In the previous session, we have studied about heterocycle nomenclature of monocyclic systems. Now we will be studying about nomenclature for bicyclic systems. So the bicyclic compounds have fused rings. They share a common single or double bond between them. They are generally named by the point of attachment between the rings. So the position 1, 2 on the heterocyclic ring is always the A phase. So this bond between 1 and 2 in this particular heterocycle. So this is the simplest one, Pyridine system. So this we are using as an example to study about how to name bicyclic systems. So the bond between, if the fusion of the other heterocycle ring happens between 1 and 2 bond, that is what is called the A phase. And if the fusion takes place between 2 and 3 bond, that is the B phase. And if it is between 3 and 4 bond, that is called the C phase. So like that we have to name the phases for this particular system. So this is mainly for the parent system. So whatever is the parent system, based on that we assign A, B, C phases. So after the name is established, the ring atoms are given new numbers for the entire bicyclic compound. So this is how the rule starts. So we will be looking at one by one elaborately. So there are various rules which we have to follow when we are going to assign nomenclature to bicyclic systems. So how do we assign basically is some of the conventions that are being used. So one of the convention is the letters for the phases, that is A, B, C for the monocycles are placed inside the ring, and the numbers for the ring positions of the bicycle taken as a whole are shown outside. So let us go back to the previous one. So as we have shown here, the phases are written inside the ring and the numbers are written outside the ring. So this is a basic convention that is being followed. So another rule says that the final numbering always begins at a position next to the ring junction. So this we have to always remember. So the heteroatom can be in any place, but the numbering generally starts from next to the ring junction. And the heteroatoms are generally given the lowest number, and we have to follow the priority rule. Oxygen gets the highest priority, followed by sulfur, followed by nitrogen, and then phosphorus. This is the rule. We can also extend this to other metals also. The position of the ring fusion generally bear the number of the preceding ring atom with the letter A attached to it. So when we are looking at the structures, we will see how we have to number them. The brackets are used around the phase letter and the name is put together without spaces, except that the dash separates the bracket from the ring number if present, as in benzo bracket B. This is the phase at which the fusion takes place. and then 1,3-thiazole. Thiazole means, thia means it is having a sulfur, azole means it is also having nitrogen. So the base unit is a nitrogen base unit containing sulfur as the heterocycle, and both the atoms are present in 1 and 3. So we will extend the bicyclic naming rules. Now these rules we have already seen in the previous session. So what we have to do is rank the nitrogen containing system over other heterocycle. In other words, any heterocycle ring having the nitrogen atom is considered as the parent one. So the suffix is always based on the nitrogen containing heterocycle. Whether it is a 3-membered ring, 4-membered ring, 5-membered ring or 6-membered ring, based on that the suffix name is given. If the heterocycle is not having any nitrogen, then the priority is given to the ring with most senior heteroatom. Generally, oxygen is the next senior heteroatom, followed by sulfur. So if there is no nitrogen, then oxygen gets the priority, followed by sulfur. And if these two rules are not applicable, then the parent ring is decided based on these sub rules. That means the greatest number of ring is considered as the base one, or the largest ring is considered as the base one. If that is also not possible, then the ring with the most heteroatom is considered as the base or the parent one, and it is followed by the greater variety of heteroatoms. These rules are basically, if there is a tie, then only we go to the next one. Otherwise, whatever is the earliest one, with that we conclude what is going to be the parent name. And the least one is the greatest number of more senior atoms will be given the parent name. Let us look at some of the examples. There are various heterocycles common name, the radical name and the fusion prefixes are given. So if it is a furon ring, then furo is the fusion prefix. If it is a purine, then it is purino. Pyran is pyrano. So if you look at very carefully in the fusion prefixes, basically O is added at the end. So this is the common thing which is added. And if it is a radical name we have to mention, then we use YL. That is, furon is furile. FUR YL is the one. And if it is fusion, it is AN is last. We say FURO, that is furo. The same way for all the different heterocycles, the fusion and the radical names are given. Say for example, the common one, thiophene, if we have to use, basically it is given the radical name as thioenyl and the fusion name is thioeno. So in the case of quinoline, it is quinolyl and quino. So these are all the different heterocycles name and their fusion and radical names. Let us take some of the examples as shown here. The compounds common names are given here: quinoline, isoquinoline and indole. But if we have to name the compound according to IUPAC nomenclature, these are bicyclic systems. So in these, all the three bicyclic systems, there is one heterocycle and one carbocycle. So that means one ring with only carbon atoms, another ring with one heteroatom. So these compounds, how do we name? So in the beginning we have seen that we have to identify what is the phase of fusion. So the phase of fusion is generally identified by going through the bonds at which the fusion actually happens. So from the nitrogen we have to start. So this is the A phase, the next one is the B phase. So in this B phase, the carbocyclic ring is attached. So this is a benzene unit. So this is given the prefix benzo, and the B phase is the place where the fusion took place, and the base ring is pyridine, 6-membered nitrogen heterocycle having only one heteroatom. So this is the pyridine ring. So how to name this compound is basically the suffix, that is the parent name, is given as pyridine. The fusion is given as B because this is the B phase at which the fusion took place, and the prefix is the carbocyclic ring or the benzene ring. So this is benzo B pyridine. And if we go to the isoquinoline, the structure between quinoline and isoquinoline is exactly a carbocyclic 6-membered ring and a pyridine unit. Both are fused together. In the first case, the nitrogen is attached to position 1. In the other case, the nitrogen is attached to position 2. So in other words, these two are isomers, basically positional isomers. So that is exactly represented in the name, because if we look at this structure, this is the A phase, this is the B phase, and this is the C phase. So the C phase is having the fusion with the benzene ring. So this compound is named as benzo C pyridine. So the isoquinoline is named as benzo Z pyridine, and quinoline is named as benzo B pyridine. And if you look at indole, this is the parent ring, here is the Pyrrole ring, so that it's a 5-membered ring. So here again, if you go with the phases, this is A phase, this is B phase. So the B phase is fused with the benzene ring, and the nitrogen is having one hydrogen. So that is the reason this compound, in this particular case, in the pyridine case, there is no hydrogen attached to the nitrogen, so the base name is given as it is. Whereas in the case of indole, that is pyrrole, we have a hydrogen attached to the nitrogen, so that is mentioned as 1H. Then the benzene unit is fused to the B phase of the Pyrrole ring. So 1H benzo B pyrrole is the name for this particular compound. So this way we can name the heterocyclic, bicyclic, heterocyclic compounds. Let us go to the next case. Here we have two rings, that is, one ring is having an oxygen heterocycle, another one is a nitrogen heterocycle. So between oxygen and nitrogen, which one will get the priority for the naming? That is a parent ring. The nitrogen ring is always considered as the parent ring, so this will be given the suffix name. And this particular ring, that is the oxygen heterocycle, is going to be named as this ring fused to the parent ring. That is how the name is going to be there. Let us see how to name this particular compound. So this is the A phase, this is the B phase, this is the C phase, and if you look at, this is the B phase fusion, and this is furon, and this is pyrrole. So roughly, if we have to name the compound, it is going to be furon fused with B phase to pyrrole. That is what is the name. Let us see how to name this correctly. So the prefix is always the other heterocycle, suffix is the one which is the parent one, and we have to talk about the fusion, which way the fusion took place. So we have to follow the same rule which we have already followed right now. So the parent ring identify, then what is the fusion we have to identify, then what ring is fused to the parent ring, the prefix. So these are all the three things we have to exactly follow, and that is nothing but furon is given as furo as the fusion name, and 2, 3 and B fusion. See, now in the previous case we do not have the second ring which is having a heteroatom. So in this particular case we have two bicyclic system having two different heteroatoms in two different rings. So this nomenclature is little bit more complex compared to the previous one. So in this particular case we have only one heterocycle having one heteroatom, the other one is a carbocycle. Here we have two rings having two heteroatoms. So this is the most important one we have to remember. The number 2, 3 is given to the attached ring. So whichever is having the highest priority, the number is given to this particular ring to give the number. The connection is from 2 to 3 bond and B phase of the parent ring. So there are two things we have to remember. One, the phase is given based on the parent ring. That is what written here. The phase is from the parent ring fusion and the number is from the fused ring, that is the highest priority ring. Because in the second rule, oxygen gets the lowest number. So in the numbering priority, oxygen gets the lowest number. So based on this, we have to give the numbering for the fusion. So this compound is going to be furan, fused between the 2,3 bonds of furan to the B phase of the Pyrrole ring. So this is the name. So the numbering goes like this. And this nitrogen is actually having a hydrogen. So this also has to be named. So in that case, this compound is named as 6H-furo-23B Pyrrole. So this is the IUPAC nomenclature for this particular compound. So whenever there is a hydrogen that is attached to the nitrogen, that also has to be included in the naming. So let us look at another compound. So in this particular compound, we have two rings, both are nitrogen based heterocycles. This is a 6-membered ring, this is a 5-membered ring. So according to the priority rules, the 6-membered ring gets the priority. So the base unit is pyridine. So this compound is basically the pyridine unit, and the attached ring is basically the pyrrole unit. So here, based on the pyridine unit, the A, B, C phase is decided, and based on the pyrrole ring, we will give the numbering. So this compound is going to be numbered as 1H, because in the first nitrogen, this gets the priority for the numbering. So this is the 1H Pyrrole. So the pyrrole ring is fused to the 2,3 position. That is, this is basically, this also is the 2,3 position. So this is 2,3 fusion, and the fusion happens in the B phase of the pyridine ring. So that is how the compound's name is given as 1H Pyrrole 2,3B pyridine. Let us continue with our nomenclature with a little bit complicated cases. So we have a pyrrole ring, we have a thiophene ring. So between these two rings, the pyrrole ring gets the highest priority. So this is considered as the parent. We have couple of types of fusion for the same compound. So in this particular case, in the first case, the compound, because the parent ring is considered as the pyrrole ring. So because this is the parent one, so the name ending, that is the suffix given, is pyrrole. And we have the thieno, that is sulfur. Thiophene's fusion name is given as thieno. And if we number this 1, 2, 3, 4, 5 and 6, on the 6th position, hydrogen is attached to the nitrogen. So 6H thieno, the fusion is 1, 2, 3. So between 2, 3, the fusion has taken place, the 2, 3 bond, and this is the B phase of the pyrrole ring. So this is the 2, 3B pyrrole. So this compound is named as 6H thieno 2, 3B pyrrole. So if you look at this compound, there is a little bit complication, because if you go by the numbering like 1, this is 2, this is 3, and this is A phase, and this is B phase. So the fusion is between the B phase, that is perfectly fine. And if we number this compound as 2,3 fusion, that is also perfectly fine. But if we go with the 2,3 fusion, then this compound and this compound, these are basically isomers. So in the first case, the nitrogen and sulfur are on the same side. In this particular compound, sulfur is at the top and the nitrogen is at the bottom. So that means these two are two different isomers. They cannot have the same name if you follow the simple rule like 2,3 ring fusion. So in this particular case, how do we actually name them? So we have to actually give this as a 3,2B. So in other words, this 3 is the first point of attachment for the fusion, and 2 is the second point of attachment for the fusion, and the fusion occurs at the B phase of the Pyrrole unit. So this compound is named as 3,2 B Pyrrole based on this particular fusion. And when we have to give the numbering here, this is 1, this is 2, this is 3, and this is the fourth nitrogen. So we have to put 4H because hydrogen is attached to the nitrogen. So this is the 4H thionyl 3,2B Pyrrole, whereas this compound is 6H because in this case the numbering goes from 1, 2, 3, and this becomes 4, this becomes 5, and this is the sixth one. So by that we can actually give the actual correct numbering under the name for both the heterocycles. And in this particular case, if we start from here, this is the A phase, this is the B phase, and this is the C phase. And if we go with the numbering here, this is 1, this is 2, this is 3. So the first point of attachment is on this side. So this is again 2,3 fusion, and this is the C phase of the Pyrrole ring. So that is given C here. And if we number here 1, 2, 3 and 4, and this is 5. So now you will be confused whether we will go with this numbering for 5H or we have to go for this fusion first, because this is a symmetric molecule, and in this particular molecule for the ring fusion we always give priority to the lowest number to reach the ring junction. So that is why the number is given as 2, 3. Whereas in the actual numbering for the hydrogen atom, we go through the regular numbering, which is outside the ring junctions are not considered in the numbering in the first case. So we have to give the lowest number, and we cannot go from here to here because there is a ring junction in between. So we have to always complete one ring first in the numbering, and then only we have to move to the second numbering. And in the numbering, sulfur gets the lowest number compared to nitrogen. So this is given the priority with number 1. So that is why this compound is named as 5H thionyl 2,3C Pyrrole. So as I mentioned here, whether it is a 2,3 or the 3,2 fusion, that is 2 here and 3 here versus 3 here and 2 here, fusion is based on the parent ring. So you have to first consider the parent ring attachment. So the nitrogen is the parent ring. So the first point of attachment is considered as 3, and not we will come from sulfur to number 2. So this is one thing you have to remember. And the connection is basically decided by the highest priority group for the numbering. And if we take the other one, which is the pyridine and the pyrrole, we have 4 different types of fusions as an example shown here, and let us look at how to name all the 4 compounds. So here, this is the A phase and this is the B phase. So this is B phase, pyridine, so that part is taken care. And here in the numbering, we have to give the highest priority to the pyrrole ring. So this gets the number 1, this is 2, this is 3, and then this comes 4. So like that the numbering goes here. And for the ring fusion, we actually have the same number here in between. If we go the lowest number to the ring fusion for the naming, this is 2, this is position 3. So the fusion is between 2, 3 of the pyrrole ring. So the name given is 1H Pyrrole 2,3B, that is the phase of pyridine. So this compound is named as 1H Pyrrole 2,3B pyridine. And if we go to the next compound, here again, this is the A phase, this is the B phase, this is the C phase. And the numbering, if we have to go, this is 1, 2 and 3. So the fusion is between 2, 3, and this is attached to the C phase of the pyridine ring. So 2,3C pyridine, and for the actual lowest numbering rule, we have to follow 1, 2, 3. So the nitrogen gets the lowest number. So this is again 1H Pyrrole 2,3C pyridine. So if you look at these two compounds are isomers, and they are obviously named with the different names. The first one is B fusion, the fusion is the same bond from the Pyrrole ring, that is 2, 3, but the phase is different. In the first case it is the B phase, in the second case it is the C phase. So that way we can actually differentiate by numbering, by the name we can identify what is the right compound. And when we go to the other next compound, so here again this is A phase and this is B phase. So the connection is at the B phase of pyridine, so that is given here. And the numbering, if we go from here, 1, 2, 3 and 4. So whether we go from this side or that side, it is one and the same. So the nearest point of connection is the third carbon. So that is why it is given as 3, 4. And in this particular case, the numbering doesn't start from here, because if we have to number this, always the ring junction is the first one to give the number. So this has to go from the nitrogen here, because the heteroatom can get the lowest number here. So 1, 2, 3, 4, 5 and 6. So this is how the numbering is given, because whenever there is a difference between the number to start from the lowest heteroatom, in this particular case nitrogen gets the priority. So that is why this is the next one attached to the ring junction. So when we are numbering, we have to always start from the carbon or the heteroatom adjacent to the ring junction. So if we go here, then the nitrogen, this will get the second numbering, but that is a wrong one, because one of the heteroatom can get a lowest number. So between these two, we have to start from this pyridine ring. So the numbering is 1, 2, 3, 4, 5 and 6H. So that is why this is given as 6H pyrrolo 3,4B pyridine. And when we come to this compound, this is a CH2 carbon. That is, this carbon is having 2 hydrogens, and this nitrogen is now completely having the no hydrogen is attached to this particular nitrogen. So this numbering will be little bit different from the previous one. So in this particular case, it is again A and B phase. The B phase is the one which is attached to the Pyrrole ring. And in this particular case, if we continue the same numbering like the previous one, the number starts from here, from the pyridine nitrogen. 1, 2, 3, 4, 5. This is 5. And this nitrogen now is not having a hydrogen, but the next carbon is having the hydrogen, the extra hydrogen. So that is why it is given as 7H pyrrolo 3,4B pyridine. So this is how we can name different heterocycles. Let us do the reverse. If a name of the compound is given and if we have to identify what is the structure, so how do we do it? So always look at what is the base or the parent name. This is given as pyridine. So the one of the ring is the 6-membered nitrogen heterocycle, and it is having the B phase that is fused with the Pyrrole unit, and the fusion is between 2-3 bonds. So this is the one we have already seen earlier. So this is the B phase which is connected to the Pyrrole ring. So this compound is called the Pyrrolo 2,3B pyridine. And another name for this one is 7-aza-indole. Here are other few examples of nomenclature for bicyclic systems. So this compound is basically, the indole is nothing but the B pyrrole, because the B ring, B phase of the pyrrole is attached to the benzene ring. In this case, the C phase is attached to the benzene. So this is isoindole or benzo C pyrrole. And when we take this compound, there are 2 benzo unit, that is carbocyclic unit, is attached to the pyrrole unit. So this is nothing but the dibenzopyrrole. Another common name for this compound is basically carbazole. And if we take the furan derivatives, this is the B fusion. The B phase is fused to the carbocyclic ring. So this is benzofeuron, that is the common name. And the IUPAC nomenclature for this compound is benzo-B-furan. So this is the furan is the base unit, benzene is attached to the B phase. So that is why it is benzo-B-furan. And this one is very similar to the isoindole case. This is isobenzofeuron. This is having the C phase that is fused to the carbocyclic ring. And the same like the previous one in the Pyrrole ring, here we have the furan ring. So this compound, the common name is given as dibenzofeuron, and if it is sulfur, it is dibenzothiophenone. And the same can be extended to thiophene derivatives as shown below. So these two also follow the same type of nomenclature. Let us move to the next topic, that is we will be studying about the basic members that are 5-membered ring heterocycles, basically furan, thiophene and pyrrole. So these compounds show aromaticity. So this is the first thing we have to study about. How do we say they show aromaticity? They all have pyrrole, furan and thiophene have planar structures. So one of the conditions for aromaticity is the compound should have planar structure, and they also have 4n plus 2 pi electrons. Here one lone pair from the heteroatom is involved in the pi bonding. That is why there are 6, 1, 2 double bonds are there. These two contribute 4 pi electrons, and one lone pair from the heteroatom, either oxygen, sulfur or nitrogen, all of them donate one lone pair. So 2 more electrons are added to this entire system. So we have 2 plus 2 plus 2, total 6 pi electrons are involved. So 6 pi electron also is aromatic in nature. Then they also show ring current in their NMR spectra. And many of their chemical properties are not typical of diene. In other words, they undergo substitution reaction rather than addition reaction. So these are all the basic criteria for a compound to show aromaticity, and these all the 3 compounds, pyrrole, furan and thiophene, show these properties. So they are also considered as aromatic heterocycles. Now let us look at the structure of all the 3 heterocycles. As we have seen, they are having a planar structure, that is a pentagonal structure, we know. So this is like a pentagon, it is there. So this is the common structure for all the 3 heterocycles. And in this particular case, all the ring and the heteroatoms are sp2 hybridized. So that is why these are called planar compounds. And each ring carbon atom forms basically 2 sp2 sigma bonds. That means each carbon, let us take this carbon, this forms 1 sp2. There is another carbon, so this forms 1 sigma bond with this particular sp2 carbon. And for this heteroatom also, this is again an sp2 hybridized atom. So this carbon forms 1 and 2 sigma bonds with sp2 hybridized atoms. And in the case of we also have one more hydrogen which is attached to this particular carbon. So we have a sp2 s sigma bond for the hydrogen atom. So there are 2 different types of bonds are there. One is like sigma bonds with the neighboring heteroatoms or the carbon atom, and sigma bond with the hydrogen atom, and we also have a pi bond. So the p-z orbital on the each ring atom forms the pi bond. That is why we say this compound is planar and it shows aromatic characters. For the formation of the pi bond, one lone pair from the heteroatom, because oxygen and the sulfur both have 2 lone pairs. Out of the 2 lone pairs, only one is involved in the aromatic sextet formation, that is 6 electron formation. In the case of oxygen and sulfur, the second lone pair basically occupies a sp2 orbital that is basically perpendicular to the pi system. When we look at the individual structures, we will see how it is actually represented. So now this is the Pyrrole unit, and the structure of Pyrrole is shown as given here. The nitrogen lone pair is involved in the pi bond formation. So we have 2 electrons from nitrogen, 1, 2, 3, 4 pi electrons on each carbon. So they all put together 6 pi electrons form the aromatic sextet, and this particular bond is perpendicular to the plane of the molecule. In the case of Pyrrole, this pi electrons are present in the p orbital, not in the sp2 hybridized orbital. So that is the only difference between Pyrrole and furan or thiophene. In the case of furan or thiophene, the second pi electron is actually perpendicular to the plane as shown here, and one of the lone pair is basically on the p orbitals, p is at orbital of the heteroatom. So these two electrons and 4 pi electrons from the carbon, they all form the pi membered 6 electron formation. So if the X is oxygen, that is called furan, and if X is sulfur, that is thiophene. So these two have two lone pairs, and one of the lone pair is perpendicular to the aromatic system. Let us study about in detail about how we get the aromaticity for the heterocycles. So basically furan, thiophene and pyrroles. We start from the carbocyclic one, that is the cyclopentadiene. This cyclopentadiene has a sp3 hybridized carbon, and the rest of all the 4 carbons are sp2 hybridized carbon. In this particular case we have only 4 pi electrons, that is 2 and 2 here. So this is not an aromatic compound, but this compound can be converted to aromatic when we convert it into a cyclopentadienyl anion by treatment with metals. Once the proton is removed, so an anion is generated. Now when the anion is formed, this again is a sp2 hybridized carbon atom. So in this particular case we have 1, 2, 3, 4, 5. All the carbons are sp2 hybridized. So due to which this compound is having planar structure. And this also has 6 pi electrons, and hence it is aromatic. And when we extend the same, that is the cyclopentadienyl anion and pyrrole, furan and thiophene, they all are isoelectronic, so they all have a aromatic nature as similar to cyclopentadienyl anion. This compound also can undergo resonance structures as shown here. The lone pair on the nitrogen can be shifted to this particular adjacent bond, and this double bond is shifted towards this particular carbon. So an anion is generated on this one. So the same way the resonance can be drawn for the entire molecule. In this resonance structure, the nitrogen is having a positive charge, and the ring carbons are having negative charge. So if you look at here, 1, 2, 3 and 4. So all the 4 carbons on of the ring can have a negative charge, and the nitrogen can have a positive charge. So these are all the various resonance structures of pyrrole. The same can be extended for furan also. But the difference between nitrogen, that is the pyrrole, and furan is nitrogen is not highly electronegative compared to oxygen. So this resonance delocalization occurs very readily in the case of pyrroles, whereas it is little bit difficult in the case of furan or thiophene. So when we study about the reactivity of all the 3 heterocycles, we do see some difference between the reactivity of pyrrole, furan and thiophene. This can be explained based on the stability of the intermediate as well as the resonance delocalization. Let us look at the dipole moment of all these compounds. In the case of cyclopentadiene, the pi bonds present here, the dipole exists in this particular direction because the electron density is high in this side, whereas here we have only hydrogen atoms. So the dipole is pointing towards the alkene carbons. So, and here the compound is having not very high dipole, it is only moderate. The dipole moment is only 0.4 dB unit. When we look at the pyrrole, it is having a very high dipole moment compared to cyclopentadiene. This is because this pi electron density on this particular carbon is very high, and here we have a hydrogen atom which is also pushing the electrons. So unlike we will be studying about furans and thiophene, where the dipole is actually pointing towards the heteroatom. In the case of pyrrole, it is pointing away from the heteroatom. In other words, this part of the molecule, that is the alkene carbons, are having more electron density than the nitrogen itself. Whereas in the case of furan, we have a completely opposite dipole with respect to pyrrole. This is because the oxygen is having a lone pair of electron, so the electrons density on the lone pair is much higher than the pi bonds. So that is why this molecule is actually polarized towards the oxygen, that is the heteroatom, and the same is the case of thiophene as well. But if you look at the dipole moment, it is much smaller compared to pyrrole. The reason is, as we have seen in the case of cyclopentadiene, there is a particular electron density higher in the alkene carbons. So that is why this part of the molecule in the case of thiophene and furan are pulling electron towards themselves, whereas the lone pair is pulling the electron towards itself in the opposite direction. So these furan and thiophene show much less dipole compared to pyrrole molecule. And in the case of nitrogen, we only have one lone pair, whereas in the case of oxygen and sulfur, we have two lone pairs. So this is one of the reasons the dipole is pointing towards the heteroatom in the case of furan and sulfur. And when we look at the electronegativity, oxygen is more electronegative than nitrogen, which in turn is more electronegative than sulfur. Here is the electronegativity values of all the elements shown here. Oxygen is having the highest electronegativity with 3.44, whereas hydrogen is having 2.22. So because of this 2.22, again the electron density is a little bit disturbed in the case of pyrrole. Whereas in the case of cyclopentadiene, which is having the electronegativity of 2.55 compared to hydrogen, which is 2.22, the difference is not much. That's why here also we see the dipole moment is not very high. And when we look at the saturated cases, the pyrrole's dipole moment exactly changes to the opposite direction in the case of pyrrolidine, because these pi bonds are now reduced, so the molecule becomes completely saturated, so there is no electron density on this part of the molecule, due to which the lone pair on the nitrogen now pulls the electron towards itself, so the molecule actually changes its orientation of the dipole from the pyrrole to pyrrolidine, and the value is also relatively high. Whereas in the case of tetrahydrofuran and tetrahydrothiophene, what happens is these double bonds are now no longer existing in these two cases. So the electron pulling by the pi bonds towards itself, that is the electron density on this part of the molecule, is completely removed. That is the reason the lone pairs are having the largest electron density, due to which the dipole moment is showing very high in the case of tetrahydrofuran and tetrahydrothiophene. So as we mentioned here, in the case of pyrrole, the sigma framework has an inductive effect towards the heteroatom. So this is a very weak one, due to which the pyrrole is having a very less dipole towards the heteroatom. Whereas in the case of pi framework, that is the resonance one, that is pulling towards the pi bonds, that is towards the carbocyclic ring. So the heteroatom is one part, the ring part which is having the carbons is another part. So due to resonance, this is pulling the electron towards one direction, and the heteroatom actually pulls the electron towards itself in a weak phase. That is the inductive effect. That is why nitrogen is having a opposite of dipole compared to furan and thiophene. And this is also very important when we want to explain the reactivity of pyrrole, furan and thiophene. So in the case of oxygen, the inductive effect is very high, whereas in the case of nitrogen, the resonance effect is more. We talked about resonance, so let us look at the resonance energies of all the three heterocycles. We will take benzene as our reference compound. So if you look at the resonance energy, benzene is having a very high resonance energy compared to thiophene, which is 122 kilojoules per mole. Pyrrole is having 90 and furan is having very low resonance energy. In other words, resonance energy can also be equated to stability also. So that means thiophene is more stable. In other words, it will undergo reaction at a lesser rate compared to furan, which we will be studying about these things later. And if we look at the electronegativities of each atoms, carbon is having 2.55, so this is also having high resonance energy. Although there is no direct correlation between electronegativity and resonance energy, we can see a small trend reflected here also. The carbon having a low electronegativity has the highest resonance energy. Oxygen having the highest electronegativity has the lowest resonance energy. Nitrogen is in between, which is 3.04, which is having a moderate resonance energy. Sulfur, which is close to carbon in electronegativity, has a very high resonance energy. So when we extend the same based on the resonance energy, the order of aromaticities, benzene is highly aromatic compared to thiophene, which in turn is more aromatic than pyrrole, which in turn is more aromatic than furan. In other words, furan is less aromatic and thiophene is more aromatic. Let us look at the electron densities around each carbon atom to see how it affects the stability and the reactivity of heterocycles, basically the thiophene, furan and pyrrole. Here is the value of electron densities observed on each atom. In the case of benzene, all the 6 carbons has the electron density 1, whereas in the case of thiophene, the sulfur is having the highest electron density because of the lone pair with 1.76, followed by oxygen, which is also having a lone pair, so the electron density here is very high at 1.71. In the case of nitrogen, this is somewhat lesser. And when we look at the alpha and beta carbons, the alpha carbon is having an electron density of 1.071 in the case of thiophene, whereas in the case of pyrrole it is 1.087. So that means this particular carbon is having higher electron density than the carbon in the thiophene. In the case of furan, it is in between thiophene and pyrrole. And if we look at the beta carbon is having 1.046 only as the electron density in the case of thiophene, whereas in the pyrrole it is very high. So in other words, this carbon is more electron rich compared to this carbon in the case of pyrrole, whereas it is the reverse in the case of thiophene or furan. Let us look at the relative reactivities based on resonance and inductive effects. The electrophile reactivity is shown here. Carbon, that is the benzene, is having less because the electron density on this particular system is lower at 1.0 compared to thiophene, furan or pyrrole. In other words, carbon's electrophilic reactivity is much lower compared to nitrogen. In other words, the electrophilic substitution on pyrrole occurs much faster compared to benzene. Sulfur and oxygen are in between the extremes. And we have seen here about the pi electron densities. Benzene is having the least electron density compared to pyrrole. Now, earlier we have seen about the inductive effect, and now we are looking at the electron densities. And if we compare these two, inductive effect and the resonance effect, if we understand the inductive effect carefully, it actually helps us to understand why pyrrole is more reactive than furan or thiophene. Because of the inductive effect, if you look at the electron density, these carbons are having more electron density compared to furan or thiophene. So pyrrole can undergo electrophilic substitution much faster compared to furan or thiophene. This is one way. But when we look at the resonance energy, it can explain the 2,5. This carbon is called the second carbon. This is the fifth carbon. This is third and the fourth carbon. So the reaction can happen at the alpha or beta position. That is what I was mentioning earlier. This is basically based on the stable intermediate. So from this particular case, if you simply look at pyrrole, this beta carbon is having the high electron density. So obviously we will think that okay, this is a carbon where the electrophilic substitution will occur relatively faster. But when we observe the product distribution, what we observe is basically on this particular carbon, the electrophilic substitution happens very fast for pyrrole. So how do we explain this? Basically, there are various factors that operate in a particular reaction. So we cannot decide based on a single parameter and say this is how the reaction actually proceeds. So we have to weigh both the effects. Basically the inductive effect and the resonance effect operate simultaneously on that particular reaction. So based on the solvent, based on the nucleophile, or based on the electrophile, or different reacting species, the product formation and the isomer formation varies. So in this particular case, the alpha carbon reacts very high in the case of pyrrole can be explained based on the stable intermediate formation, although it cannot be explained based on the electron density. So we have to be very careful, and this is one of the reasons when we talk about reactivity, we are only talking about relative reactivities. And basically the nitrogen is inductively electron withdrawing, so that also plays a role in how it actually undergoes reaction. So in this particular case we have more electron density on pyrrole compared to less electron density on thiophene. So this is clearly reflected in the electrophilic reactivity. But the product distribution basically depends on the resonance as well as inductive effect. Now let us look at or recap what we have studied so far. So we have studied about the electronegativity difference between thiophene, furan and pyrrole. The furan is having a very high electronegativity, followed by pyrrole, then thiophene. But the electronegativity is no way related to how it actually the compound undergoes reaction. And if you look at the resonance energy, thiophene is more stable and furan is less stable. So in other words, if we simply look at resonance energy, we will be thinking that furan will undergo reaction much faster compared to pyrrole, but that is not the case. And if you look at the stability of the intermediate, this is a stable, thiophene forms a stable intermediate, furan also forms a stable intermediate, but pyrrole forms a highly stable intermediate, because if an electrophile adds to this system, that is actually a positive charge has to be developed on this particular ring. Nitrogen can have electropositive nature much better than the more electronegative oxygen or sulfur. In other words, nitrogen can stabilize a positive charge much better than oxygen and sulfur. Due to that, the electrophilic substitution occurs in pyrrole much faster compared to thiophene and furan. And if you look at the dipole moment, pyrrole is having the highest dipole, but in the opposite direction. So in other words, this also helps us understand why these carbons are more reactive in the case of pyrrole, whereas in the case of thiophene they are less reactive. So we have to invoke various factors to explain the product formation in a particular reaction. So in other words, many factors affect the reactivity. So please don't consider there is only one effect operating for a particular reaction. Let us look at general synthesis of heterocycles. The formation of heterocycles, some of the common methods are shown here. One is a nucleophilic ring closure. In this case, formation of a acyclic starting material to a cyclic product is studied. The next one is formation from a lesser ring, that is one ring less. That these two are nucleophilic ring closure reactions. We also have electrophilic ring closure reactions, ring closure by way of cyclic transition states, conversion of one heterocycle ring to another one, modification of an existing ring. So these are all the common reactions by which heterocycles can be formed. In the case of nucleophilic ring closure, the reaction of two halogen or acyl halide with ZH2 gives the cyclic system. So X or X, there are two halogen atoms attached to the one of the starting material which reacts with the ZH2. Z is the heteroatom under consideration. So this gives a cyclic system. Another case is reactions of Diketo compounds with ZH2. So here there is a carbonyl unit, there is a carbonyl unit. This reacts with, there is a central alkyl unit which is connecting these two keto units or the carbonyl units. And we have ZH2. This gives a cyclic system RZ as shown here. If the carbonyls are separated by 2 carbon, that is 1,4-dicarbonyl compounds are used, we get a 5-membered cyclic system. And if the carbonyls are separated by 3 carbons, that is 1,5-dicarbonyl compounds, we get 6-membered cycle, heterocycle. In the case of nitrogen, the ZH2 may be dash NH2, that is an amine can be used. And when 2 heteroatoms are required, hydroxylamine, hydrazine, hydrogen peroxide can be used because this is OH, this is NH2, NH2, this is NH2OH. So 2 heteroatoms can be incorporated using these kind of reagents. In the case of electrophilic ring closure, the reactions are little complicated because oxygen, nitrogen and sulfur cannot act as an electrophile because these are electronegative elements, so they cannot act like an electrophile. So in these cases, the carbon atom of the future ring only can act as an electrophile. So that means when we do need an electron-rich aromatic ring for these kind of cyclization reaction to occur. So this is here aniline is one such example. In this particular case, this is the electron-rich aromatic system, and this can undergo different cyclization reactions. Like this is a formation of quinoline. We will be studying these kind of reactions later in this our course. So basically, for the electrophilic ring closure to occur, we do need a electron-rich aromatic system as one of the component. And the ring closure using cyclic transition state, basically these are Diels-Alder type reactions. So here we have given some examples of diene and the dienophile. So the heteroatom can be on the dienophile or heteroatom can be on the diene. So they undergo cyclic transition state to give the cyclized product. So this is a general method of preparing heterocycles, and in this particular case this is applicable for 6-membered rings. And another method is conversion of the heterocycle to another one, that is preparation of pyridine from tetrahydrofurfuryl alcohols and ammonia, that is a ring expansion reaction. This is shown here like tetrahydrofurfuryl alcohol when treated with ammonia gives pyridine. This is a 5-membered heterocycle, gives a 6-membered heterocycle. So this is a ring expansion reaction, and in the case of photochemical we can use both ring expansion and the ring contraction is possible. In this case a 3-membered ring is converted to a 5-membered ring, and the rearrangement of ring atoms are also possible. So these are some of the examples. And the other reactions include modification of an existing ring, that is dehydrogenation of aromatic heterocycles with sulfur or with palladium heterocycle. And we can also use the examples of ring formation, that is intramolecular cyclization with concomitant removal of the leaving group to give a 3-membered ring, or as shown here the 4-membered ring. So these are some of the ring formation reactions. In summary, let us recap what we have studied so far. We have studied about the nomenclature of bicyclic systems, how to name heterocycles having more than one ring. We also studied about the aromaticity, where we studied about the structure and the resonance energies of various heterocycles, mainly the 5-membered rings. We also studied about how the electron density is distributed around the ring. And we also studied about the relative reactivities of furan, pyrrole and thiophene. We also studied about some of the general methods of synthesis of heterocycles. With that, we conclude this session. Thank you.